one by one, round-robin style. Each party will keep their questions to 5 minutes or less. We have a timer to help you stay on track. Given that there are 6 parties to the hearing, we should have time to accommodate 2 rounds of questions per party. That goes for all panels. I'll make all rulings on the admissibility of exhibits, appropriateness of questions, and pertinence of proffered testimony. If a party spokesperson objects to any question asked during the hearing or wishes to discuss the admissibility of an exhibit or the pertinence of proffered testimony, please raise your hand and wait to be recognized by me. A word about conduct. This is not an adversarial hearing. The board does not permit cross-examination of witnesses in the legal sense, nor do we permit questions related to fault, outside litigation, or legal liability in general. Such questions are not relevant to the fact-finding purposes of an investigative hearing conducted by the NTSB or our statutory mission. This does not mean difficult questions won't be asked. They will be, and they should be. This is an investigation. We are here to improve safety. That is our sole focus. So with that, Dr. Bauer, please describe the exhibits.
Thank you, Chairwoman Homendy. Exhibits for this hearing include reports produced by NTSB investigative staff, videos, and other documents submitted by the technical panel members, witnesses, and parties to support the testimony and questions you will hear over the next 3 days. The exhibits for this hearing are in the docket. The docket number is SA-544. That's Sierra Alpha 544. The NTSB is authorized by statute to disclose information to carry out its mission, but we protect confidentiality and proprietary information to the extent possible. As such, the exhibits contain redactions. These are the results of negotiations between the parties and the NTSB regarding the disclosure of information claimed to be personally identifiable, security sensitive, or proprietary in nature. Though redacted, the exhibits contain sufficient information so that members of the public can refer to them during the hearing and throughout the NTSB investigation. The exhibits entered into the record in any presentations, along with other records of the investigation, become part of the NTSB public docket and are available via the NTSB website, ntsb.gov. The public docket opened this morning. Party spokespersons and witnesses have been provided electronic copies of the public docket containing the exhibits identified above. The docket is located on the investigation page, which you can access in one of 2 ways: by visiting ntsb.gov, or if you've joined us in person, you can scan the QR code on the hearing agenda. On the investigation page, you will find the link to the public docket on the right-hand side, just below the map. A transcript of the testimony taken during the hearing will be prepared and entered into the docket as soon as possible. In addition, Mr. Baranovsky will keep a list of any documents admitted during the hearing that are not currently exhibits in the NTSB public docket. These documents will be submitted after the hearing and entered into the docket. As a reminder, if a party to the hearing has a new exhibit to propose in accordance with 49 CFR section 845.9, it will not be admitted unless the chairwoman determines that a good cause has been shown. While parties do not participate in the analysis of evidence, parties can submit written comments for our consideration. This is where parties can state their views for the record, such as the potential conclusions that may be drawn. we strongly encourage the parties to submit written comments, which are beneficial to our analysis. Our regulations provide 2 separate opportunities to do so. First, parties may submit comments on the hearing. Per 49 CFR Section 845.13, following the investigative hearing, any party to the hearing may submit proposed findings to be drawn from the testimony and exhibits, a probable cause, and proposed safety recommendations designed to prevent future accidents or incidents. The proposals shall be submitted within the time specified by the investigative hearing officer at the close of the hearing and shall be made part of the public docket. Parties to the investigative hearing shall serve copies of their proposals on all other parties to the hearing. Such comments are due to me, the hearing officer, within 30 calendar days after the close of the hearing, by September 1, 2025. We ask that any submissions be sent to us electronically. The second opportunity to submit comments is through the traditional party submission process outlined in 49 CFR Section 831.14. Any party to the investigation may submit to the NTSB written proposed findings to be drawn from the evidence produced during the course of the investigation, a probable cause, and/or proposed safety recommendations designed to prevent future accidents. A due date for this submission will be provided by the investigator in charge at a later time. Parties may avail themselves of one, both, or neither of these opportunities. If you do send comments at any point, they will be included in the public docket. As mentioned, we will consider party comments during the analysis phase of the investigation and in the preparation of the final report. Chairwoman Hamady, that concludes my remarks.
Thank you. And just to reiterate, those comments for the hearing due 30 days from the close of this hearing, September 1st, 2025, by September 1st. Thank you so much, Dr. Bauer, for going through that. And I'm now going to turn it over to Bryce Banning, our investigator in charge, to provide an overview of the accident.
Morning, Chairwoman Hamady and members Inman and Graham. I'll begin my presentation with an animation. The animation is about 11 minutes long and will cover a summary of the event, depict the flight tracks of the accident, aircraft, and show air traffic control communications as well as helicopter inter-cockpit communications. There will also be audio associated with the communications mentioned. The animation will conclude with an airport security video of the accident aircraft in flight and ends immediately when the collision occurs. Events after the collision are not represented in the video. We realize that some attendees and remote viewers may find this animation and security video difficult to view and hear. We would like to take a moment to allow those currently in the boardroom to leave for the duration of the video, or turn away from your screens if viewing remotely. We will inform you when the animation and video are finished playing. We will begin the animation now. On January 29th, 2025, about 8:48 p.m. Eastern Standard Time, a Sikorsky UH-60 Lima helicopter operated by the United States Army and a PSA Airlines CRJ-700 collided in flight approximately 1/2 mile southeast of Ronald Reagan Washington National Airport, or DCA. The 2 pilots, 2 flight attendants, and 60 passengers on board the airplane, and all 3 crew members on board the helicopter were fatally injured. The military helicopter flight originated from Davison Army Airfield, Fort Belvoir, Virginia. The flight was an annual evaluation for the pilot with the use of night vision goggles. The airplane was operated by PSA Airlines, doing business as American Airlines Flight 5342, a scheduled domestic passenger flight under Title 14 of the Code of Federal Regulations, Part 121, from Wichita, Kansas to Washington, D.C. Night visual meteorological conditions prevailed at the time of the accident. In the radio communications, the accident airplane was using call sign Blue Streak 5342, and the Army helicopter was using call sign Pat 25. The Federal Aviation Administration provides charts that specify helicopter routes to facilitate operations in high-traffic areas. The helicopter routes have no defined lateral boundaries, but they do have maximum altitude limits. The helicopter routes are depicted by a blue line on the Google Earth image. Helicopter Route 1's western section begins in Cabin John, Maryland, and follows the Potomac River southeast to Washington, D.C., through the Tidal Basin and the Washington Channel to Haines Point, and then turns east along the Anacostia River. At the time of the accident, Helicopter Route 4 intercepted Route 1 at Haines Point and continued south along the Potomac River's eastern shore past DCA and the Wilson Bridge. North of Chain Bridge, the maximum altitude is 1,300 feet. Between Chain Bridge and Key Bridge, the maximum altitude is 700 feet. Between Key Bridge and Memorial Bridge, the maximum altitude is 300 feet, and south of Memorial Bridge to the Wilson Bridge, the maximum altitude is 200 feet. At 8:33 p.m., 15 minutes before the collision, Pat 25 requested permission to travel from Cabin John along Helicopter Route 1 to Helicopter Route 4 to Davison Army Airfield. The DCA local controller approved the request.
Pat 25 is looking for Cabin John, Route 1, Route 4 to Davison.
Pat 25 approved.
There was no communication between Pat 25 and the DCA local controller for 12 minutes. At 8:39 p.m., 9 minutes before the collision, Flight 5342 was cleared for the Mount Vernon Visual Runway 1 approach to DCA by Potomac Terminal Radar Approach Control. Select in-cockpit communications between the instructor and the pilot in Pat 25, primarily about altitude, will be shown on a black background in the animation. At 8:43 p.m., 5 minutes before the collision, Flight 5342 was handed off to the DCA Tower Local Controller. The local controller asked the crew of Flight 5342 if they could switch their approach from runway 1 to runway 33.
Bushview 5342, Washington Tower 1 star 32017, gust 25. Can you take runway 33?
The crew accepted the change and they were cleared to land on runway 33. This magnified satellite photograph shows the locations of runway 1 and runway 33 at DCA.
Yeah, we can do 33 for Bush 5342.
Bushview 5342 at the Wilson Bridge, change to start for runway 33, runway 33, clear to land.
Change to runway 33, runway 33 for land, Bush 5342.
There was no further communication between the local controller and the crew of Flight 5342 before the collision. The following animation shows the positions and altitudes of the accident aircraft for the final 3 minutes before the collision. An altitude profile view of the two accident aircraft is also displayed. Audio of the air traffic control communications will be played during the animation. The local controller was operating on 2 channels. While all aircraft could hear the local controller, helicopter crews could only hear radio transmissions from other helicopters, and airplane crews could only hear transmissions from other airplanes. Only communications between the local controller and PAT 25 will be shown in text on the screen. The controller twice advised the crew of PAT 25 about the conflicting traffic on approach and circling to land for runway 33. Both times the crew of PAT 25 reported that they had the traffic in sight and requested to maintain visual separation. The controller approved the request both times.
PAT 25, traffic just south of Wilson Bridge to CRJ at 1,200 feet, start from runway 33. This separation approved. American 1630 Tower, runway 1, lot void traffic throughout, start from runway 33, this traffic on 6 mile funnel.
Flight up runway 1, American 1630. Tower muscle 7, approaching Springfield, request route 3. Runway 1.
Most 7, stand by. Bushview 5307, keep rolling out to November, ground 47, good day.
November 307. National Tower, good evening, Air Carrier 1 with single medevac.
American 1630 1 star 32014, gust 25, traffic 2 mile left base, runway 33, no delay, runway 1 clear for immediate takeoff.
Number 1, cleared for takeoff, American 1630.
Muscle 7, is there a request?
Route 3 to zone 6.
Most 7, you say route 3 to zone 6? Most 7 approved.
American 472, National Tower, good evening, Air Carrier 1 with single medevac helicopter 1,000 feet, 29901 on the altimeter, requesting zone 6 for Fairfax.
Medevac Air Carrier 1, Washington Tower, National Altimeter 29900. Approved through Washington class, Robert Space Portland, Sheridan to Fairfax.
29990 for Air Carrier 1, copy.
PAT 25, get the CRJ in sight. PAT 25, pass behind the CRJ.
This club has a aircraft inside precision separation.
This separation.
The following video shows the airplane and helicopter leading up to the point of collision. The video was recorded by a camera located near the approach end of runway 33 at DCA, oriented to the south. The video shows the night lighting conditions and the appearance of the aircraft lights against the cultural lighting of the city. Aircraft lined up on approach to DCA can be seen in the right corner of the screen. The flashing lights identify the touchdown zone of runway 33's landing threshold. Flight 5342 is visible in the upper left corner as it approaches runway 33. PAT 25 appears from the left side of the screen, moving to the right as the two aircraft cross flight paths. This concludes the animation.
Thank you, Mr. Banning. We're going to turn to the first panel. So, Dr. Bauer, will you please provide an overview of the panel topics and introduce the technical panel and the witnesses?
Chairwoman Hamady, the first panel is overview of the accident helicopters, air data systems, and altimeters. The panels will address helicopter static pressure and pressure altimeter systems, static system error and instrument error of the altimeter, total error effects on the accuracy of barometric altitude, military and civilian design requirements for helicopter air data systems and altimeters, design challenges for helicopter air data systems and altimeters, helicopter altimeter accuracy, standards, checks, and verification, and how accuracy of parametric data is verified and maintained for both civil and military flight data recorders. The NTSB technical panel, starting on my right, is composed of Mr. Chihoon Shin, aerospace engineer, helicopters, Ms. Marie Moeller, mechanical engineer, vehicle performance, Mr. Sean Payne, branch chief, vehicle recorder division, and Mr. Michael Portman, aerospace engineer, recorder specialist. Witnesses for panel one are composed of the following individuals, starting from my left, nearest the board members. Mr. Dan Cooper, Senior Technical Fellow for Avionics, Systems Integration and Test with Sikorsky. Mr. Lance Gant, Chief Scientist and Technical Advisor for Rotorcraft with the Federal Aviation Administration. Chief Warrant Officer Colleen Lewis, Department of Evaluation and Standardization with the U.S. Army. Mr. Steve Bradham, Chief Airworthiness Engineer with the U.S. Army, and Mr. Scott Rosengren, the UH-60 Chief Engineer with the U.S. Army. Chairwoman Hamady, these witnesses have been pre-qualified and their respective experience and qualifications appear in the docket as exhibits.
Thank you, Dr. Bauer. Will the witnesses please stand? Please raise your right hand and answer by saying, "I do." Do you swear or affirm that the testimony you will give in this hearing will be the truth? Thank you. You may be seated. As a reminder to the witnesses, you'll remain under oath until the conclusion of the hearing. We ask, and this is very important, we ask that you answer questions factually. Please avoid analysis or any speculation. If there's a question about the question, if it leads to speculation or you think it might, just direct the question to me and I'll make sure to clarify. Also, I'm going to ask our staff, we've already talked, but just a reminder, and then also the witnesses, please do not use acronyms. We all use it frequently, but there are a lot of people, both in the audience and watching virtually, who don't know what those acronyms mean. So we want to make sure that they can follow along. So please try. I know it'll happen, of course, but if we can try and do our best, I think that would be much appreciated. Finally, you have microphones ahead of you, so just push the microphone button to talk and push it again when you're finished. Thank you so much for being here, and I'll turn it over to Mr. Shin.
Good morning. We will begin panel 1 of this investigative hearing with a presentation from myself and Ms. Moeller. The purpose of this panel is to discuss the air data system and altimeters on the UH-60L Black Hawk helicopter. Investigators identified discrepancies related to the accident helicopter's altitude, leading to additional investigative work to determine the validity of the altitude information displayed to UH-60L pilots and the altitude data recorded by the helicopter's Flight Data Recorder, or FDR. To begin, it's important to start with some definitions of altitude, which is an aircraft's height above some reference point. In this image, there's an example of 2 different ways that altitude can be measured: above mean sea level and above ground level. We will discuss pressure altitude, which is then corrected to height above mean sea level, and radio altitude, which is measured by bouncing radio waves off a surface below the aircraft to determine its height above ground. A third type of altitude, GPS geometric altitude, will also be referenced. Generally, atmospheric pressure decreases with increased altitude. The air is thinner on top of Mount Everest compared to near sea level, such as Washington, D.C. The International Standard Atmosphere Model, or ISA model, defines an altitude for a baseline pressure of 29.92 inches of mercury at sea level. If you measure the static air pressure around an aircraft, it can be compared to the ISA model to determine how high the aircraft is. However, as you know from weather forecasts, atmospheric pressure can change, so a correction factor for local atmospheric conditions is needed to be applied to more accurately determine an aircraft's height above sea level. A barometric altimeter is essentially a barometer that measures static air pressure and displays an altitude in feet. The image on the right shows a UH-60L barometric altimeter. Local atmospheric conditions that necessitate a correction factor can be applied to the altimeter using a barometric adjustment knob. This local altimeter setting corrects the ambient pressure altitude to the helicopter's altitude above mean sea level. The barometric setting for the altimeter is shown on a 4-digit counter in the altimeter setting window, also known as the Colesman window. Local altimeter settings are broadcast on Automatic Terminal Information Service, or ATIS, and by Air Traffic Control, or ATC. Multiple cockpit instruments, including the barometric altimeter, measure static air pressure surrounding an aircraft as part of their function. Static ports supply static air pressure to these instruments via a series of tubes. Static ports can be located on the fuselage as shown in the yellow arrows in this image. Static ports can also be incorporated into a pitot tube, which is called a pitot-static probe. The UH-60L helicopter, as shown in the image on the right, has 2 pitot-static probes that are located on the left and right sides of the cockpit roof, immediately aft of the cockpit doors. The UH-60L helicopter has two independent static systems, identified as Static 1 and Static 2. Each pitot-static probe has one port for its pitot system, 2 ports for its Static 1 system, and 2 ports for its Static 2 system. The right pilot's barometric altimeter uses static air pressure from the Static 1 system, while the left pilot's barometric altimeter uses static air pressure from the Static 2 system. The simplified diagram on the right shows how the Static 1 system supplies static air pressure to the right pilot's barometric altimeter. An air data transducer also uses static air pressure supplied by the Static 1 system. Outputs from the air data transducer are used by multiple helicopter systems. One of these systems is the remote data concentrator, which receives uncorrected pressure altitude data and supplies that data to the Integrated Vehicle Health Monitoring System, or IVHMS, which includes the Helicopter Flight Data Recorder, or FDR. Next, Ms. Moeller will discuss the pressure altitude data from the Black Hawk's FDR that was analyzed for this investigation.
With that explanation of pressure altitude and barometric altimeters, I'm now going to discuss the altitudes recorded by the accident helicopter. This plot shows the FDR recorded pressure altitude in blue for a portion of the flight. The blue dotted line is the pressure altitude corrected for the local altimeter setting. The red line is what we determined to be the actual height above sea level of the helicopter based on radio altitude and terrain, which will be discussed further in the next slide. The Army crew was trained to fly the helicopter routes around DCA using the barometric altimeter. The triangles show 3 pilot altitude callouts recorded on the CVR during this portion of flight. Altitude callouts showed a possible lower than actual altitude understanding by the crew. To explain how we determined the helicopter's actual height above sea level, I'm going to start by walking through the altitudes recorded by the accident airplane. The CRJ recorded 3 types of altitude measurements: pressure, radio, and geometric. As discussed at the beginning of the presentation, radio altitude is measured by bouncing radio waves off the terrain below an aircraft, and geometric altitude is determined by GPS satellite triangulation. These 3 types of altitude are shown in this plot as recorded. Like pressure altitude, radio and geometric altitudes must be corrected for local effects. When these 3 independently measured altitudes were corrected for local conditions, they showed good agreement by being within 10 to 20 feet of each other, confirming they were reliable measurements of the airplane's height above sea level. After some additional checks at known ground locations, the CRJ's altitude was considered well validated. This plot shows the CRJ's corrected pressure and radio altitudes as solid lines, and the Black Hawk's corrected pressure and radio altitudes as dotted lines for the end of the flight. The Black Hawk was not broadcasting to ADSB, so no geometric altitude was available for comparison. For the final 5 minutes of flight, the helicopter was flying over the tidal portion of the Potomac River, so the radio altitude would be equal to the height above sea level. Additionally, later testing of similar helicopters, which will be discussed next, showed good agreement between geometric and radio altitudes while over the river, adding an additional level of confidence to the radio altitude's accuracy. While the radio altitudes of the CRJ and the helicopter, which are shown as red lines, were within 10 feet at the approximate time of impact, the helicopter corrected pressure altitude was 100 feet lower than the CRJ's corrected pressure altitude. This picture shows the instrument panel of a UH-60L. On the right side of the image, the radio altimeter is circled in red, and the barometric altimeter is circled in green. The discrepancies between the radio and pressure altitudes recorded on the accident flight data recorder and questions about what altitude was displayed to the crew based on their altitude callouts led to a series of altimeter tests. 3 UH-60L helicopters from the same battalion as the accident aircraft flew a formation flight where the right seat pilots wore cameras to record the instrument panel. After the flight, the data recorders for each helicopter were downloaded for comparison to the in-cockpit instrumentation videos. This led the lead helicopter was broadcasting to NTSB, so geometric altitude for that aircraft was also recorded. The altimeter testing found that on the ground, before the engines were started, the barometric altimeters of all 3 helicopters were within 20 to 45 feet of the field elevation, which would be considered within tolerance. Once the main rotor was producing enough lift to hover, the barometric altimeter readings dropped significantly and were lower than the helicopter's actual on-the-ground elevation or hover altitude. Notably, the barometric altimeters continued to be 80 to 130 feet lower than the helicopter's determined altitude above sea level when flying at speed over the tidal portion of the Potomac River later in the test. Additionally, the corrected pressure altitude recorded on the data recorders did not match the video captured barometric altimeter readings on the ground for any helicopter, but did show good agreement when flying over the Potomac for 2 of the helicopters. The results of the flight test led to on-ground tests of the pitot-static systems for each helicopter. For these checks, the pitot-static probes are connected to a test rig that simulates set altitudes by increasing or decreasing the pressure the probes see. The altimeters on 2 of the test helicopters performed well. On the 3rd helicopter, the altimeters still performed within or near the tolerance, but were less accurate. So, while the altimeters showed an 80 to 130 foot differences in flight, they were within 20 to 55 feet under a controlled test environment. A helicopter's rotor system produces the lift and thrust that allows it to fly. The wind that you feel when you are near a helicopter taking off is the downwash produced by the rotor, which changes the air pressure around the fuselage of the helicopter, making it challenging to measure an accurate static pressure to determine altitude. The controlled environment of the pitot-static ground checks eliminated all rotor downwash effects, and those results also matched the flight test altimeter readings that were made before the engines were started. But once the helicopter rotors were turning and producing lift and thrust, the altimeter readings lowered significantly and stayed lower throughout the flights. In summary, we found discrepancies between the FDR pressure altitude and determined height above sea level for the accident helicopter. Subsequent testing showed discrepancies between the cockpit barometric altimeters and the determined height above sea level on 3 other UH-60Ls. The objective of this panel is to learn more about the design of pitot-static systems and the altimeters, the unique challenges in designing such systems for helicopters, and how the accuracy of these systems is determined and maintained. Another objective of this panel is to learn more about how parametric data, particularly from the air data systems, are validated for flight recorders. This concludes our presentation. Mr. Shin will now begin questioning.
For the witnesses for this panel, we'll ask our questions in 3 distinct topic areas: air data system design, pilot operational considerations with the barometric altimeter, and air data accuracy for flight recorders. So we'll start with air data system design. Mr. Cooper, can you please describe some of the engineering considerations on the placement of static ports on a helicopter?
When placing the pitot and static ports on a helicopter, you must first consider the total set of customer requirements, and then consider the complex flow dynamics, as was shown in your presentation, that occur throughout the whole flight operational regime of the aircraft.
And when you say customer requirements, can you expand on that, please? What that could entail?
For example, they have where they're going to operate. So if they have to land in austere conditions, sand, grass fields, have to consider impacts to material entering the probes or damaging the probes. Must consider maintenance operations on the aircraft. If the probes are placed lower, there is risk, of course, to the maintainers bumping injury as well as damaging the probes. And then another area that needs to be considered, what other sensors are populated on the aircraft? Those sensors have their own needs for placement to meet their performance requirements, and they can create disturbed airflow in themselves in different locations that, of course, would affect that probe location.
And Mr. Cooper, how does the location of the static port affect the cockpit instrument readings during different regimes of helicopter flight, such as hover, cruise, sideways flight, backwards flight?
It's a function of the static position error that exists in those different regimes of flight. So the helicopter has, of course, a wide operational movement, forward, rear, sideward, rearward flight, as well as side slip limits. The static port placement must be able to handle the whole regime, although accuracy is normally presented in forward flight.
And Mr. Cooper, how are the aerodynamic effects of the cockpit instrument readings due to placement of the static ports identified during the design phase for the air data system?
When this aircraft was originally designed in the late 70s, placement was done by experience and general practice. Military helicopters from Sikorsky at that time placed the probes over the cockpit and was generally found to meet the requirements. Of course, today, computational fluid dynamics could be used to analyze, but in the late 70s, that was an opportunity. So the placement is made, and then flight test is utilized to gather the data to identify the resulting error of that placement.
And is there a design target for the amount of difference between indicated altitude and the actual altitude for the helicopter when designing a system?
Can you clarify, please?
So for the difference between what's indicated in the cockpit instrument to where the helicopter is actually at for altitude, is there a target during the design phase that you try to achieve for the placement of the ports for certain airspeeds?
For the UH-60, it would be based on any government requirements.
And what about for commercial helicopters that Sikorsky has designed?
Again, it depends on the category it's being certified. FAR 291325, provides guidance for static position error, as well as it provides wording that you must use a certified altimeter.
Okay. And with the complex flow environments that we've identified that are present with helicopters in designing these systems, can you please describe some of the mitigation strategies that may be used to account for these aerodynamic effects that you see in the indicated altitude?
For the Black Hawk, at the time it was designed and with the government requirements that were provided, really probe geometry, placement, its installation angles is the primary tool. The UH-60 government requirements specified a specific altimeter to utilize. So that would not make the altimeter indication system an option to address any corrections. Present day, of course, with advanced equipment, air data computers give you more of an option. But again, 1970s, late 70s, that was not available, and the government requirements specifically called out the altimeter to be used, and it was provided as government furnished material property.
And Mr. Bradham, how would the Army evaluate mitigation strategies developed by a manufacturer?
Yeah, so typically in flight test, but if I could just back up for 1 second and just to clarify, so for a pedostatic system, we talk about instrument error, which is the actual calibration error in the physical altimeter itself, and that's what you're checking when you check on the ground without the rotors turning. And then you have what is called position error or installation error, which is the error caused by aerodynamic effects around the aircraft. And those are two independent errors with different standards. And I would say the standards that the Army used and the standards that the FAA uses for civil aircraft are very similar, and these issues are not unique to military aircraft. But your question is how would we evaluate that? And you do an airspeed calibration in flight test, and that airspeed calibration determines, for a given flight condition, determines the position error of the pedostatic system, and then we can mathematically convert that into altimeter error, and we can assess that against a standard. So for the Black Hawk, the position error, that standard was a mil spec called mil-I 6115, which has a very similar, slightly more stringent standard than Part 29.
And if a helicopter did not meet that military standard, would there be a required redesign, or would there be a correction factor that gets applied that pilots have to utilize? This question is to Mr. Bradham.
Yes, I think that would depend very much on the specific circumstances. There were, looking back through the historical documents, there were cases where there were small out of spec issues. One knot over a standard in one place, and the decision is made, by the government and the contractor that there's no further action required there. They can provide a correction to the operator when that's necessary, but again, I think it would depend on the particular flight condition and the particular size of and the effect of the noncompliance.
Mr. Cooper, for the UH-60L helicopter, the pedostatic probes are placed above the cockpit, which is closer in proximity to the main rotor. What are the technical considerations that would lead for those pedostatic probes to be placed closer to the main rotor?
In line what I stated before, it's a balance of the total set of requirements. So again, for a military utility helicopter operating in the landing conditions it does, placement of the probes lower, as I said, could expose it to ingress of material, danger to maintainers, damage during ground operations. So that would tend to give guidance, provide an alternative by putting it above the cockpit, as was done on other military models, Sikorsky and others produced at that time.
And Mr. Gant, can you describe how the FAA approaches certification of static systems and barometric altimeters on civil helicopters?
Yeah, so as mentioned previously, for altimeters in civil transport category helicopters, that is regulated by Federal Aviation Regulation 29.1325. altimeters. And the expectation is that the applicant for certification would comply with all the requirements within that paragraph, including the position error requirements that are in there. There are allowable tolerances.
And from the FAA's perspective, would there be a concern with the placement of the pedostatic probes as seen on the Black Hawk?
I don't have any opinion on that. I think there's different ways to design, just as you've shown in your presentation. Maybe typical today is more on static port locations on the fuselage, but there have been many instances where static ports are also co-located with the pedo system. So again, it comes down with compliance to the requirements and not necessarily the aspects of whether that's incorporated one way or the other.
And Mr. Cooper, aside from customer requirements, what would be other technical considerations to select a pedostatic probe versus a pedo probe with a separate static port that's on the fuselage?
Again, I sorry to come back to it, but it is the total set of requirements. In that picture you showed for the fuselage placement, that was a Naval Hawk aircraft, a Sikorsky-produced Naval Hawk aircraft, but it does not have a requirement for a sliding cabin, or also known as the gunner's window. So that area would be covered when the gunner's window is in the open position as it can be in flight. So that would take that location, that example you've shown. It comes down to available real estate, the dynamic conditions in that area. In your discussions with me earlier, you mentioned tail ports, static ports, but again, there's equipment on the Black Hawk that would impact that operation. It's considering all the requirements that the helicopter must meet, what's fitted to achieve that, and what available area on the fuselage can be utilized, and then with that, understanding the dynamic conditions that may be present on that fuselage if it's static, if it's suitable for a static port.
And Mr. Bradham, aside from the static 1 and static 2 systems on the Black Hawk, are there alternate static sources?
No, not on the Black Hawk. The S1 and S2 are redundant, and each static system, as you mentioned in your presentation, pulls from each side's pitot tube. So S1's fed from both right and left, and S2's fed from both right and left.
Okay. Can you please, Mr. Cooper, this question's for you. Can you please describe the types of errors that can add up to ultimately affect the indicated altitude on the barometric altimeter?
As was stated by the other gentleman, there's two prime areas. One of them has several contributions, but there's the static source error, and then there is the instrument error. The instrument error for this altimeter has several factors that builds up to its estimated error. Instrument error, consider a tolerance. There's a plus and minus. So when you come up with that error, there could be in the plus direction or the minus. Static source error, which is identified, the resulting is identified during flight test. It's usually a number as a function of airspeed, and it is not constant, but I would not call it a tolerance. There's not a plus or minus. There is a number that's identified during flight test as a function of airspeed.
And Mr. Bradham, from the airworthiness perspective, how are the stack up of these errors managed by the Army?
So for the, from an airworthiness perspective, right, we have standards for each of the individual errors as they occur. So instrument error, so for the altimeter itself was handled for the Black Hawk by mil spec. It was a mil spec. It was 81852 and 81851, and that lays out a number of individual tests under specific conditions for a number of specific errors. So, for example, inside the altimeter, there's two separate calibration tests, one for the Colesman window gearing and one for the expanding aneroid capsules, and there's different standards for those, and those are independent errors. So we don't have a standard to roll all that together. We do it by each individual error that occurs to make sure it meets tolerance, and I believe that's how it's done, not just in the Army. But then you have position error, and as I said, that's a mil spec 6115 alpha, which has a standard for that. So, and then, so that's how we manage it. Each one of the errors has its own tolerance defined. And there's corresponding civil standards. The FAA has a TSO, a technical standard order, that defines altimeter instrument error, and FAR Part 29 talks about altimeter position error, same as the mil specs used to.
Mr. Cooper, can you tell me about other designs for barometric altimeters? In this case, the accident helicopter's barometric altimeters uses aneroid wafers or capsules, as Mr. Bradham mentioned. Can you tell me more about other designs that ultimately allow for higher precision and accuracy for barometric altitude or pressure altitude?
So first, the time period, that was a common design. And as I said, the government requirements, that altimeter was specified to be used and was provided by the government. As time has gone on, and certainly current day, air data computers became available, which provided they did not have the mechanical wafers, the mechanical indicating dial. They did not have the mechanical correction for the Colesman window. So those errors could come out. So the implementation of air data computer, which requires a different display medium, allows you to achieve a lower error at the instrument error analogy.
And Mr. Bradham, what are the factors that are considered in transitioning existing helicopters to newer technologies such that Mr. Cooper just talked about?
From an airworthiness perspective, we're just looking to see if it meets all the standard requirements. I would say that, the Army and DoD, we've moved away from the very prescriptive mil specs, and we use commercial standards more typically going forward.
And Mr. Gant, from the civil helicopter side, at what point do the design requirements warrant transition to newer technologies that we're talking about here with air data computers?
Well, we don't prescribe when a new technology has to be introduced unless it's one that we think would improve safety to the extent that we would go through the whole process of rulemaking to make that technology available, or a requirement, excuse me, in the federal regulations.
And Mr. Gant, with changing operational requirements in the national airspace key into that decision of whether rulemaking is needed to require newer technologies?
I would say it could factor into that.
And this question is for both Mr. Cooper and Mr. Bradham. Aside from rotor wash considerations, what other challenges are there in designing an air data system that provides accurate indicated altitude to the pilots?
I go from my perspective, the main issue is low speed operation, right? And that's the influence of the rotor wake, which is what you talked about, right? It's why you see, when an aircraft picks up to a hover, why you see the altimeter decrease, right? It's the rotor wake coming down on the static system, and that's at low speeds, common to helicopters, that can be an issue. It's why the Black Hawk pressure instruments, really below 40 knots aren't used. So I think that's the primary issue, but the configuration of the aircraft can affect the static position error.
Yeah, for low speed, it is obviously the rotor wash, but at more forward speeds, that rotor wash is not impinging on the probe, so that is not a factor at the higher speeds. Certainly above 60 knots normally is where we don't see that effect. Again, depends on the install, but it is the configuration of the aircraft, what else is installed, either originally or as the model has been utilized, and certainly the customer has updated configuration of the aircraft. So installation of items can have an effect on the static position error.
Thank you. I'll hand it off to Ms. Mueller.
Good morning. Mrs. Lewis, when flying at low altitudes, do you normally reference the radio or the barometric altimeters?
In my experience, when flying at low altitude, I would be referencing the radar altimeter.
And when would you transition roughly between the two?
In my experience, certainly 200 feet and below, I would be referencing the radar altimeter. However, if I was flying on a published MSL route, I would be referencing barometric altitude.
Ms. Lewis, can you go over the procedure for setting up the barometric altimeter and checking it before flight?
Yes, as part of the cockpit equipment checks, the barometric altimeters are set on the ground before the aircraft is started, and the requirement for the Army is that they are within 70 feet of field elevation.
And where do you get the barometric setting from, usually?
From ATIS, the Automated Terminal Information System.
Thank you. Mrs. Lewis, what reason might you flag your barometric altimeter as being inaccurate?
Aside from the initial check on the ground, in my experience, the only reason I would have to question my altimeter would be if ATC were to call me and question what altitude I was flying at, if I was supposed to be flying at an assigned altitude or on a route at a particular altitude.
Okay. So moving gears a little, Ms. Lewis, what other helicopters have you flown?
I have flown the Alpha, Lima, Mike, and Victor versions of the Blackhawk, and those are the only helicopters that I have flown.
Okay, thank you. So on those other models, have you seen any differences between the Lima model and those helicopters for the barometric altimeter?
Can you clarify the question, please?
Okay, so when you're at hover in that flight regime, have you seen between like the Alpha to the Victor and the Limas different, like do they feel different? Like what is being displayed on the barometric altimeter?
In my experience, I'm not referencing the barometric altimeter to hover. I would be glancing inside at the radar altimeter while at a hover. I would not be paying much attention to the barometric altimeter at a hover.
Okay, thank you. Mr. Bradham, could you please describe the standards related to the design of the static system for the Army helicopters?
Yeah, absolutely. And I think it's important, of course, to point out again that the standards are very similar between military and civil, particularly the ones used for the Blackhawk. And so we'll talk about all the different kinds of error, right? So the standards, you have a standard for the instrument itself, which was the mil-spec 81851 and 81852, which have the same tolerance. And that has a number of different tests inside it, a number of dynamic tests for things like hysteresis and friction. But I think the main ones to focus on here are the two calibration tests. You have a scale error test, which is where you test the calibration of the capsules themselves. And then you have a barometric scale setting test where you test the calibration of the Colesman window gearing itself. So you have standards for each one of those, and those standards vary by temperature and they vary by altitude. So for example, in the scale test, the standard at sea level, standard temperature is plus or minus 30 feet. But at 500 feet, that's plus or minus 35 feet. It changes. At extreme temperature, that can go to as far as 60 feet. And then the barometric scale setting is generally plus or minus 25 feet, but it too changes. And that's very similar to the FAA TSO, which is based on a Society of Automotive Engineers standard. And then you have the position error standard. As we talked about, that's for aerodynamic effects on the system, and that's in this case that was from MIL I 6115, which is plus or minus 25 feet per 100 knots of airspeed, and that's very similar to Part 29, which is 30 feet per 100 knots of airspeed. And then I'll just mention it here, just that if you compare radar altimeter to baro altimeter, you have to keep in mind that radar is measuring true altitude, like if you put a tape measure out the aircraft to the ground. Pressure altitude is measuring a pressure altitude based on a temperature assumption, and so you have to correct for non-standard temperature as well. Thank you.
Thank you. So, Mr. Cooper, what amount of difference between the barometric altimeter and the helicopter's actual height is expected for UH-60L?
Based in my review of the government requirements prime item development spec, I've not found a standard cited for static position error, not defined. Instrument error is identified by the MIL specs that were cited, 81852 and 8851. The MIL spec that was cited, 6115A, was identified in a report, but have not found it defined in the government requirements. So ultimately, the resulting error was identified by flight test.
So those identified by flight tests, and we've kind of already talked about this a little bit, but the error changes at different regimes and different flight regimes.
So yes, the flight test data is presented as altitude error as a function of airspeed. So it is not necessarily constant number. And as in the report for the UH-60 Alpha, which the configuration is the same for the Lima, it is changing for the clean configuration, so I can't give you a singular number. For the configuration, it's called high drag. It's when the external stores support system, also called ESSS, and we often, at least in this course, we call it ESSS, so there's a lot of acronyms used there in case I say it again. That also has a different static source error curve. That one is more consistent, though, and is a nominal above, I believe, 40 knots is a nominal 50 foot. I'll have to check on the speed, but it is, as you stated before, as is the clean, higher in a hover, but in forward flight, it's a nominal 50 in that configuration.
Thank you. Oh, and just for people who are listening, the ESSS, or the picture of the accident helicopter, the wing tanks out the side. Right. So how does Sikorsky manage that difference in altitude? What is it that you produce for the operator and the crew?
So the flight manual is approved by the Army. Its content is that which is approved by the Army. In the report of the test I cited, in that document, it recommended that the curves for the altitude, position error for the clean, as well as the high drag external storage support system be included in the flight manual, but it ultimately was not included in the approved version.
Thank you. So, Mr. Bradham, Mr. Cooper was just saying about how the flight manual discusses the differences for the clean configuration helicopter, but it didn't make it into the Army flight manual, the differences for the ESSS system.
I'm sorry, just clarification, both altitude errors
Both
are not
sets
in the
of
final.
altitude errors,
Just
sorry.
for clarification.
Do we believe that crews should be informed of this difference?
So for the external storage support system for ESSS, yeah, that level of position error between 80 knots and 100 knots of about 40 to 50 feet, that level of position error was identified, you know, in the original qualification of the system. We verified that level of error exists through the L. We've looked for records of the discussion. At the time, there would have been an operator's manual content review board, and we've looked for a record of the discussion about altitude. We've not found a record of a discussion about whether, you know, about a decision to include or exclude that information. I think it's important to put that information in context when you're thinking about what to provide to an aviator. In particular error has no influence. Spec, and you know, in my experience, typical aircraft separation distances are 500 feet or more. So it would be, I'd be speculating if I went to the reason of why put that in record.
Now that it's been identified, do you plan on including it?
I say we've been tasked by the program, the Airworthiness Authority has been tasked by the Program Office for Utility Helicopters to do the analysis, which we've done, and to provide a recommendation back, which is being done right now, which will then go to the PM office for their consideration as to how to whether and how to incorporate it into the manual.
Thank you.
Thank you.
Mr. Bradham, do you have the time frame for when that will be completed?
No, I can't speak to the program office in terms of the timeline. We've been.
Steve, or Mr. Bradham, I can speak to that.
Thank you.
I'm the division chief of the Utility Helicopter Programs Office. I was the one who tasked Mr. Bradham's organization to take a look at this issue. So typically we have a 30-day turnaround on tasks to the organization. We're about week 2 of that. And that's about the time we found out about this issue. And so we should have something back this fall at the latest. And then we'd be happy to keep you appraised of that status.
Thank you. And I also ask that you bring your mic closer to you. Thank you.
Will do.
All right, Ms. Lewis. During our investigation, we saw the 80 to 130 foot differences between the barometric altimeters and then the radio and the geometric altitudes. Would you, as a pilot, consider this amount of difference impactful to your operation?
In my experience, a difference in 80 feet or so between the radar altitude and the barometric altitude would not be cause for alarm. Generally, I'm relying more heavily on one altitude instrument versus the other, depending on what I'm doing and what altitude I'm at. So I'm generally not looking at both and trying to figure out the difference between the two, depending on what I'm doing on that particular flight.
All right, this is for Mr. Cooper, Bradham, and Rosengren, just to start. But during the ground testing of the 12th Battalion helicopters, 2 of the helicopters, the barometric altimeters were within 20 feet of tolerance. But once we were in forward flight, with 100 knots of forward speed, the barometric altimeters showed errors of 80 to 130 feet. What types of errors do you believe could contribute to this 80 to 130 foot discrepancy?
Yeah, I'll start with that one, please. So when you think about all the different errors that could contribute to that, one, you have to make sure the Colesman window is clearly set correctly, and that the Colesman window actually reflects the right barometric pressure. So the flight tests you're referring to are the ones on the 15th of May, that 1-unit flight. So backing up, it's important to point out that that's really an anecdotal event. It doesn't use the standard flight test methods that the military and the FAA would use in order to characterize a pedostatic system. So there's not an independent truth measurement of barometric pressure and some of the other things that we would use here. But so in terms of the errors, one is the Colesman window. Then you have the instrument error, which is what you saw on the ground. All three of those aircraft were registering altimeter low on the ground, but within spec, right, for the instrument error. Then you have the position error. So 2 of the aircraft were clean, and 1 of the aircraft was ESSS. So the clean aircraft at 100 knots, you're looking at about roughly 7 feet altimeter low in position error. For the ESSS aircraft, about 50 feet position altimeter low for position error. And then you also have to correct for non-standard temperature, because you're trying to compare radar altimeter to barometric altimeter. And so that wasn't a factor for the accident aircraft because the conditions were close to standard and you were low altitude. But on the 15th of May, those flights, you were flying at about 1,000 feet and about 9 degrees hotter than standard based on the aircraft OAT. That's about 36 feet altimeter low. So the combination of those factors, the instrument error, the position error, and a temperature correction, which all happen to be in the same direction, doesn't always happen that way, but in this particular case did, that if you carry that for the 3 aircraft, those errors ends up bringing you to relatively good agreement between rat out and bear out, if you compare them that way.
Thank you.
And I concur with all the statements that were made. Just one clarification, because I was involved in that ground evaluation. One of the aircraft, the right altimeter, did fall outside the Army maintenance manual check limit, so that was out of spec, and in fact, its vibrator was inoperative. So that right altimeter data would be in question for that aircraft.
Thank you. Mr. Rosengren, do you have anything to add?
No, I just, the only comment I have there is whenever Mr. Bradham and I kind of went through the data, pursuant to some of the questions I think we'll have later, I was properly educated and pleasantly surprised. We was able to get to doing the air stack ups within 1 foot of the differences, and so we'd be happy to provide that data to you in writing later.
We would definitely appreciate that. Thank you.
Yes, ma'am.
So continuing on that, and you were talking about how it is anecdotal, and we do recognize that 3 helicopters is quite a small data, is a very small sample set, but it did line up with the existence of a possible wider discrepancy. And you have looked into that, clearly. Is there additional testing planned between the Army and Sikorsky?
So from an airworthiness perspective, we've gone back through the data, and we have airspeed calibration data for the Lima. We understand the static position error. So we don't have any flight testing planned. I'd leave that to the program office if they have other thoughts relative to that.
Yeah, no, as I mentioned earlier, I was as initial receipt of the data from the flight test and anecdotal flight test you mentioned, I wanted to look into it, and I asked Mr. Bradham's organization to please let's get together and try to understand what's going on here to see if there is an issue. And again, after stepping through all of the various sources of error, and again, it's a very piece-part manner, everything was within specification minus the discrepancy we've tasked them to look into. And so I don't see any need from a safety or airworthiness perspective to do any changes for the Lima helicopter. From my perspective, I advise the colonel who advises the Army the safety of the aircraft. My perspective is this is a safe aircraft.
Yeah, and we can, if you'd like, we can talk to the difference between the recorded pressure altitude in the IV in the recorder. Yeah. Oh, cool. Thank you.
So this conversation makes me conclude that this feels like this is an inherent limitation of a barometric altimeter.
That based on all the information we've worked together and along with our Sikorsky friends, I believe this is the expected errors in an altimeter system. So when we provide that data to an aircrew, there should be an expectation, as I believe they're trained to have that expectation, plus minus 100 feet or so.
Thank you very much. This is the end of my line of questioning, and Mr. Payne will begin next.
Get my microphone positioned here. Hello. I'm going to follow on with specifically pilot operational considerations, and we talked a bit more about stacking errors, and we touched upon setting the Colesman window correctly. I'm going to come back to that. So I'll start with Ms. Lewis, and I'll have some questions for Mr. Bradham also later, as he's an experienced Black Hawk pilot, is my understanding. Ms. Lewis, earlier you described briefly setting the altimeter, your operations around that area. As a pilot, can you walk us through in detail the process of setting the altimeter according to the Army's operational procedures?
Yes, as part of the cockpit equipment checks, the barometric altimeters are set generally based off of the local ATIS information, and then it's compared to the known field elevation. And as long as there's not more than a 70-foot error, then the altimeter is considered reliable for flight.
Sure. I want to get into a bit of a discussion about the known field elevation. So you cross-check, obviously. Once you've set the altimeter according to the ATIS, there's a 70-foot allowance. My next question goes into, how do you determine the field elevation for those who are unfamiliar in the audience? Where do you get that data from?
Field elevation is published on airport diagrams. It's published on approach place. It's published in a number of places for airports that we operate in and out of.
Sure, for operational airports. So continuing on with maybe where your unit was based, is it tribal knowledge or an official part of Army procedures to discuss if there's changes in elevation between where the measurement is taken, which for FAA airports typically at the highest point on the runway, if you're starting or performing that check, as you said, prior to rotors turning, are you do the Army's procedures account for a difference in the airport topography when you make that check and try to fall within the 70 feet?
The Army procedure is to check tower setting against the setting for field elevation, and then it's unreliable for flight if more than 70-foot error exists.
Sure. Okay. Can you recall a circumstance where the published field elevation varied significantly from where you initiated the checklist procedure in your career?
As part of the checklist procedure, we don't attempt to determine if the elevation is different based on where the aircraft is parked. We base it off of the field elevation.
Okay. I'm just going to we talked about field elevation being published at FAA or, some kind of, whether in another country there's published data available. What if you're at a remote or unfamiliar airfield, you're operating there? Is there another resource you might use other than published chart, or would you rely on the topography of the chart itself in that situation?
I would rely on the known field elevation if there was one for where I was landing and taking off from. And in my experience, I would have generally departed from somewhere where I had an altimeter setting And if I did not know what the field elevation was or was unable to determine it, I would maintain that altimeter setting until I was back in location to receive an updated altimeter setting.
Okay, noted. Yeah, I'm just trying to approach the situation from as many angles as possible. When you're flying in the national airspace system versus flying on deployment outside of the national airspace system, for example, do these procedures change at all, or there's more emphasis done in the NAS versus on deployment, or does it remain the same?
There's no difference in how we approach setting altimeters when we're operating in the national airspace system versus on a deployment.
Okay, thank you. I'm going to incorporate Mr. Bradham into this line of questioning as well, so I just want to totally lean on Mrs. Lewis. So, Mr. Bradham, during flight, how would a pilot determine the barometric altimeter is erroneous and unreliable?
Yeah, so in my experience, the only time we've done that in flight, right on the ground check, if you had a significant difference, between the right and the left side in the ground check before you took off. And I want to point out that ground check exists. The FAA uses that same, in the Airman Information Manual, uses a similar check with plus or minus 75 feet. But yes, and in flight again, if there was a significant disparity between the right and left side while you were flying, and I mean a significant disparity, more than 70, 80 feet, right? You would make note of that and come back. But if ATC contacted the aircraft and said, "Hey, you're not at your right altitude," and we were, according to our instruments, that then would be cause for concern. But otherwise, and I've, in my experience, I'm trying to recall if that's ever happened to me where I've had a barometric altimeter problem like that, and I don't recall one.
Okay. Yeah, Ms. Lewis, you previously mentioned being queried by ATC. Have you ever experienced that in your career, or thought to a situation where you might want to question whether or not the left and right side altimeters were comparable?
I have not had an experience in my career flying the Black Hawk where the barometric altimeter, if it passed the checks on the ground, was unreliable.
Okay, thank you. Let's say hypothetically you had a crew and the two pilots did detect an offset between the right and left baro altimeters. I'll start with Ms. Lewis. What would they do? And then as a follow-up, would there be anything in the Army's operational procedures that would require the pilots to make a report or report it to maintenance?
If there was a discrepancy between the left and the right pilot's altimeter, are you asking which altimeter we would use?
Well, no, not which you would use, but you've detected this discrepancy. It's more than 70 feet. Is there a requirement to report that then to maintenance, your command, make a note of it somewhere?
Yes, if there was a greater than 70-foot difference, that aircraft would not be flown. It would be placed on a grounding red X condition and be taken out of service until the altitude discrepancy was addressed.
Okay. I'm going to come back to this question, and you touched on it previously. You said you preferred a different altimeter for different type of operation, different flight regime. In Army procedures, is there ever an operational area where you would cross-check between the barometric altimeter and the radar altimeter?
In my experience, in a situation where I was flying close to the ground, maybe 500 feet and below, if I was supposed to be at an MSL altitude, but I was flying low to the ground, in my experience, I would be referencing or cross-checking both instruments in that situation.
Okay. I understand it would be difficult because it would depend on where you're operating. If you're over sea level, obviously that calculation's much easier. Getting more into a bit of an acuity discussion. So it's discussed in our internal investigation. If you're flying in visual conditions during the day, what would the altitude visually that the pilot could recognize, would 100 feet difference be something that pilots are trained to know visually without reference to any instruments versus maybe 1,000 feet? Mr. Bradham or Ms. Lewis can take that.
Yeah, I'll give my experience.
Yeah.
And when you're very low to the ground, that's true, right? To be able to tell the difference between 100 feet and 200 feet, I would say yes. But, at a much higher altitude than, the difference between 4,000 feet and 4,100 feet, no.
Right. Yeah, exactly. If you're at higher altitude, also you can maybe tell difference of thousands versus lower. Let's see. Would this change at night? If you were, low-level flight, you'd say, I can tell the difference between 100 and 200 feet. At night, would you expect that calculation to be the same? I'll ask Ms. Lewis.
It's always more difficult to determine your altitude when flying at night, but I agree with what Mr. Bradham said, that if you're very low level, 200 feet and below, it's a little bit easier to determine, but even at 1,000 feet, 100 feet of difference is not something that in my experience, that I'd be able to accurately determine.
Sure, and then a quick follow-up there. If you're wearing night vision goggles, I guess, can you expand on the possibility of doing that under NVG at low level?
NVG's low level, if I have, it would help if there were known obstacles that I knew the height of as I was flying in the area out to the left and right of the aircraft. It really depends on what environment I'm flying in, what obstacles are there, buildings. It would really just depend on where you were flying out, how easy it was to determine a difference in 100 feet of altitude when looking outside the aircraft.
Okay. Yeah. Yeah, go ahead.
Just to follow up on Mr. Payne's question, for both Mrs. Lewis and Mr. Bradham, if you were flying in day visual conditions, could you notice a difference between flying at 200 feet versus 300 feet?
That's a difficult question to answer. From my experience, I would have to say that would depend very much on the terrain that was around and how familiar I was with that terrain.
I would agree with that statement. It would depend on where I was flying, and as I mentioned previously, if I knew the height of some of the obstacles or perhaps building or terrain in the area.
So to clarify, if you were not familiar with the terrain that you were flying through, then what does the answer change?
Can you just restate the question once just to make sure
If you're not familiar with the terrain you're flying through, could you pick up on a difference visually looking out the window between flying at 200 feet versus 300 feet? Is there enough of a difference at those altitudes?
Yeah, that's a difficult question to answer. I'm not sure if you'd be able to resolve that difference.
I agree. I don't know that I could 100% accurately determine the difference in altitude.
And my question was for day, so just to confirm my understanding, at night and under NVGs, it would be even more difficult to make that distinction?
Yes.
Thank you.
That was my kind of operations-related section. I'm going to shift gears slightly for my last few to Mr. Cooper, discussing some differences between the Mike and Lima model. So, Mr. Cooper, please describe the pedostatic system design on the Mike model. Sorry, for the audience, the Mike model would be a newer version of the helicopter. If you want to just expand on that rather than me explain why don't we just talk about the differences as well?
Again, it has its own set of requirements, to their vehicle, different engines, different, more capable rotor blades. So, but from an air data system, it utilizes the same pedostatic probes in the same location as the Lima. That is unchanged. It employs air data computers, ADCs. There is less plumbing because there are no, I will call them analog instruments equivalent to what is in the Alpha or Lima. So those probes feed directly, they feed the air data computers. The air data computers feed multi-function displays with digital data. And then those same ADCs through a redundant path provides air data information to the flight controls or any other subsystems within the aircraft which needs that information. There are two ADCs. Each go to their respective pedo probe, and the static, just as with the Alpha and Lima, is crossed. So there's the redundancy there.
Okay, so in summary, you've replaced, you said, well, older analog digital systems, there's less tubing because you have two ADCs and a glass panel display. I guess my ultimate question would be, given the differences between the Lima and the mic, would you expect more accuracy out of the mic versus the Lima in terms of displayed altitude?
Again, we talked about static source error and instrument error. I would expect improved accuracy for the instrument error aspect. The static source error is not changed.
Thank you. I'm going to pass the microphone over to Michael Portman, aerospace engineer from the Flight Recorders Lab. He's going to discuss air data accuracy for flight recorders.
Thank you very much. All right, good morning. So yes, as Mr. Payne mentioned, I'm going to start my questions with some design requirement questions for flight recorders. So I'll start with Mr. Gant on the civil side. What requirements exist for flight recorders in civil helicopters?
So for flight data recorders, there's a requirement in Part 91, which are the general operating rules, that if you are operating a multi-engine turbine-powered helicopter with a seating or passenger capacity of 10 or more, you must have a flight data recorder that records the parameters that are contained in an appendix. I think it's Appendix E, but of Part 91 that lists all the parameters as well as the accuracy requirements for those parameters.
Okay, and that was for Part 91. Are there equivalents in other operating parts as well?
Yeah, Part 135 has a very similar requirement for, again, multi-engine turbine air-powered helicopters with 10 or more passenger seating capacity. There's another break if you have a helicopter that carries 20 or more. There's a different FDR requirement, but still one.
Okay. Can you expand for a moment on, you mentioned that included in these appendices, there's also standards for accuracy of the data. Can you expand on that a little bit, specifically if you know anything about the altitude data?
Yeah, I think in the Part 91 Appendix E, I'll say the standards as I read them are fairly loose. I mean, for accuracy for the altimeter, I think it reads from anywhere from plus or minus 100 to up to plus or minus 750 feet with a resolution of, I can't remember, either 130 feet or 150 feet on readout.
Thank you. One more question for you, Mr. Gant. What methods does the FAA require to ensure the continued accuracy of recorded flight data?
Yeah, so there's no specific rule that says how often you need to be, I'll say, interrogating a installed FDR to see if it's still providing realistic data. However, in the technical standard order, as well as in our advisory material, it is incumbent upon either the manufacturer, the FDR, or the installer to come up with a maintenance program. And then our recommendation in the advisory material and AC 21-141B is that a reasonableness check for the FDR should not exceed being done beyond 18 months.
Okay, thank you very much. Turning to Mr. Rosengren. So looking at the design of the flight recorder system on the UH-60L, it's my understanding that the system was added after the initial production of the UH-60L. Can you just explain a little bit about when that occurred and what the motivation was for installing that system?
Yes, sir. So it was we call it a commercial off-the-shelf or COTS solution that we bought for the Integrated Vehicle Health Monitoring System, IVHMS. It included both a health and usage monitoring system, so a PCMCA card that a data card. I can't tell you what PCMCA stands for. A data card that you could pull out and download the parametric data that's also sent to the flight data recorder that we used for accident investigation, such as this. And so that IVHMS, the Integrated Vehicle Health Monitoring System, produces COTS. It was around the mid-2000s. So in 2005 and 6 is when we consulted with our who we purchased this. Component and DO-178 were considered to make sure that and so when we did the modification work, we got an airworthiness release from the Airworthiness Authority, the modification work order to and then before we went through the installation.
Okay, and then I'll follow up specifically on the parametric data side of things. Did you have any standards or ideas that you had for what sort of things you wanted to be recorded, or what accuracy you wanted those things to be recorded with?
So the main reason we were putting the system on was twofold. It was for the health and usage monitoring system, which as the gentleman referred to, is our maintenance program that we use. So we download those parametric data after each flight or weekly. And we take a look at the data, make sure it mainly there for regime recognition. So by regime recognition, that's where we try to determine how the aircraft was flown, so that if we have any particular parts lives that are depending on how aggressive or non-aggressive you fly the aircraft is dependent, then we can determine that from the parametric data that regime was in, and then we can decrement the parts lives appropriately.
Thank you. Next question. Which standards, or are there standards that exist that the Army uses or requires for the accuracy of the recorded flight data on the UH-60L?
So we had a digital source collector operation requirements document back from 1996. We'd be happy to provide that if we haven't done that already. And in that standard, it was encouraged to have a commercial off-the-shelf solution, for which we did. So we didn't give the vendor we bought the commercial off-the-shelf solution from a data accuracy requirement. We did to make sure that since it was commercial off-the-shelf, we made sure that it met the airworthiness requirements, but that it was capable to do the health and usage monitoring system requirement, as well as the flight data recorder function.
Thank you. Can you describe how the Army verifies the function and accuracy of the flight recorder upon installation?
Yeah, so at the end of the modification work order, there's a maintenance test flight that's performed. And as that maintenance test flight is performed, we have a maintenance operations check and MOC. And in that MOC, we record what the displayed altitude or other parametric parameters are select not all, but a select some. And I'd be happy to provide that table to you. And then we record what was recorded in the parametric data.
All right, and then a follow-up to that. Can you describe similar thing, how the Army ensures the continued function and accuracy of the flight recorder in operation?
Sure. So as I mentioned, each time the particular installation has occurred, we do those maintenance test flights and we do the MOCs to make sure that the installation was successful. As we improve the system over time, we went through a substantial upgrade back in 2008, where the original 2005 system did not have an integrated flight data recorder. So the 2008 version, we put the integrated flight data recorder, of which we have the configuration today. We've had several software upgrades. During each software upgrade, they do a system integration lab test at the factory to make sure that the software performs as designed. And then we go through a similar airworthiness analysis of the MWO with the updated software. And then that MWO is then updated. And again, each time it's installed, we do the maintenance test flight and then do the maintenance operation check at the end to make sure that the data is correct.
And just to clarify, are there any requirements for downloads at certain times specifically to verify the function and accuracy of the recorded data itself?
So we download the data at the end of each flight. It's available for download and put into our data warehouse that we monitor through artificial intelligence and other means to make sure that the data is reasonable. And so that's performed on a regular basis.
And is that specifically for you mentioned for doing, usage and vibration analysis and whatnot. Is that specifically for that, or is it to look at a broad spectrum of parameters?
Yeah, there's three specific parameters we look at. I can get to those particular parts, but there's three specific parameters we look at to make sure that the vibration data is not over any exceedances. And if those particular parameters are over exceedances, then we do an on-condition change to those parts.
All right, thank you. Moving on to some operational questions, although I am going to stick with you, Mr. Rosengren.
Yes,
how is the flight recorder data used within the Army? I know you'd mentioned that it's mostly used for this vibration analysis. Is there any other example of, or any times that you can think of where download of the FDR data or the flight recorder data of any type has been performed for reasons other than those you had mentioned?
In the operational Army, there hasn't been. There has been programs over the years where we try to do a flight operations quality assurance type of effort. So those efforts have been done where we've used the downloaded data to do flight recreations, mission rehearsals, those sorts of things. But that never got out to the operational Army.
Okay. Can you describe how the data is downloaded?
Sure. There's the data card that gets pulled out of the system, and then that's taken to an aircraft notebook, a laptop computer, and you input into the laptop computer, and then there's a procedure to extract the files and get it into the cloud-based system where we store our data.
Another question for you. When looking through the data, we did notice that that there is no GPS global positioning system data that is recorded on the flight recorder. Can you just explain why that is?
Yeah, as was mentioned before, the 60 Liam is an analog aircraft, and so when we did the modification work order and the installation to put the system on the aircraft, we got the signals that were available, and those signals were not available for incorporation into the integrated vehicle health monitoring system.
Thank you. One last question as I'm wrapping up, this time for Mrs. Lewis. On the UH-60L, the air data transducer provides pressure altitude information to the heads-up display. I'm curious, in your experience, have you ever done a cross-check while using the heads-up display between that altitude and the altitude that's in the barometric altimeter?
Sir, in my experience, using the heads-up display would be for low-level flight under night vision goggles, and I would not be referencing barometric altitude in my heads-up display.
All right, thank you very much. I'll turn it back over to Mr. Shin.
Mr. Fuchs, can you pull up Exhibit 7 Kilo Juliet, page 23, for the witnesses, that's the presentation backup slides that has the diagram for the right barometric altimeter and the uncorrected pressure altitude that it feeds to the helicopter's transponder for the UH-60L, and how that pressure altitude data gets transmitted to ATC ground radar and also out to ADSB. So, Mr. Bradham, on the UH-60L, if the right barometric altimeter provided inaccurate altitude indications, regardless of the source of the error, would the transponder transmit that inaccurate pressure altitude through the to ground stations?
Yeah, so the transponder on the right side has an encoder, and the encoder sends a signal in 100-foot increments, and that signal is based on pressure altitude, so it's referenced to 2992 as the Colesman window. So if the pilot made a mistake and put the wrong Colesman window setting in, or the setting was not indicative of the true static pressure, that error would not be transmitted. But any other errors in the system would be transmitted. But the encoder is transmitted in, it's only in 100-foot increments. So, yeah. Cool. Thank you.
And Mrs. Lewis, for the UH-60L, are there procedures for what pilots should do with the transponder's functions if they detect that the right barometric altimeter has become unreliable during flight?
For the UH-60 Lima, the transponder is required for flight. So if there was an issue with the transponder, the aircraft would return to whatever station it departed from, and that issue would be addressed before flight was continued with that aircraft.
I'm sorry, if I may, could I just add one point, that the encoder, it's sending in 100-foot increments. It changes at the 50-foot mark, but the standard is at the 50-foot mark plus or minus 40 feet. So it can be 90 feet off inside its specification. Thank you.
And Mrs. Lewis, to clarify, if the right barometric altimeter was determined to be unreliable during the flight, knowing that it transmits its encoded altitude to the transponder, is there any procedures to disable the altitude reporting function on the transponder, or do you just leave it alone?
There's no published procedure for addressing that I'm aware of.
And would you notify ATC of the discrepancy that's identified if flying in the National Airspace System?
I would.
Mrs. Lewis, going back to one of the previous questions about cross-checking between the left and right altimeters, and this is a question that Mr. Bradham can answer as well. Is there a published procedure for pilots to cross-check between the left and right side for accuracy between the two altimeters?
The check is against field elevation. It's not between the two altimeters. So the 70-foot error, if field elevation was 0 feet, one could be 70 feet and the other one could show minus 70 feet. So it's not an error between, it's not checking for error between the two, it's the setting against field elevation.
Yeah, no, I concur.
And if there was a discrepancy between the left and right barometric altimeters identified during flight, let's say on the order of 100 feet, Mrs. Lewis, how would you verbalize that, or how would you triage that with the other pilot?
If there was a difference of around 100 feet, 100 feet, that's to maintain within 100 feet of altitude is the standard for us flying. So if it was right at about 100 feet, that would not give me much cause for alarm because it would still be within the standard of maintaining altitude within plus or minus 100 feet.
Mr. Bradham, when you were saying the additional 40-foot change on the transponder altitude, do you have documentation of that you could provide?
So the encoder standards, it's mil-spec 81852. which was the mil spec for the altimeter. When you in the encoder section, it says the standard is at the 50-foot mark plus or minus 40 feet from that. And so it's in mil A 81852. It's paragraph 356. And under encoder, it said the switching point shall be at altitudes 50 feet plus or minus 40 feet removed from the nominal indicated altitude.
Thank you very much.
Thank
And
you.
Michael Portman has another question.
Sorry to circle back. Just one last question for Mr. Gant. In Part 135, Appendix E, you had mentioned that there were standards for accuracy, in this case for altitude, that can vary between plus or minus 100 feet to plus or minus 700 feet. Can you clarify that those standards are plus or minus 100 feet that is recorded on the FDR as compared to what?
I would have to defer that question to get back with you folks.
Okay, thank you.
All right. Mr. Gant, the FAA has several restricted category UH-60L helicopters that are approved for civil use, including the Lima model. What are the static system and barometric altimeter design requirements for these restricted category helicopters?
So the FAA regulations for bringing in surplus military aircraft that have been designed and manufactured for use by the U.S. military, given a satisfactory operating history, which usually is at least 10 years, if they are surplus and they are determined to be airworthy by the FAA, they can come into the system utilizing, I'll say, the military records as well as military flight manuals. There will be no additional showing to the FAA to bring those aircraft and put them on the registry under restricted category. And under restricted category, that severely limits operations, mainly to agricultural, external load operations, and forest and wildlife management, which usually translates into firefighting operations.
Mrs. Lewis, can you just clarify for us, when flying low level, what would be the primary instrument you would reference for altitude?
The radar altimeter, in my experience.
And would that change when flying on a helicopter route with a ceiling?
If it's a published MSL route, I would still be referencing radar altitude, but I would also be taking barometric altitude into more consideration than what I normally would be if I was flying at a low altitude, if that makes sense.
Okay. And is that so if I understand you correctly, you'd be referencing low altitude on a MSL route with a ceiling. You'd be referencing both the rad out and the barometric altimeter.
Yes.
And is that trained or is that a personal technique?
There's no standard for which instrument I would be looking at, but if I'm on an MSL route, I would have to be at some point referencing the barometric altitude to maintain the route altitude.
Okay. Thank you. Yeah, my question, I think, really was, is that a procedure that's trained in the Army to cross-reference those two instruments, one on a route of that nature, or is that more of a personal technique for you?
I would say that's more of a personal experience-based technique for me, but also coming back to if I'm on a published MSL route, the only way for me to maintain the prescribed altitude for that route would be to utilize my barometric altimeter as well.
Understood. Thank you.
Chairman Hamady, that will complete the technical panel's questions.
Thank you very much. We're going to take a 15-minute break. We'll be back and start promptly at 11:35.